MEG 224, Engineering Mechanics Dynamics. Lecture 4, Kinetics of Particles, the Principles of Work and Energy, Part B. And it can be found in chapter 14 of Engineering Mechanics Dynamics by R.C. Hibler. Objective of this lecture: we're going to develop the principle of work and energy and apply it to solve problems that involve force, velocity, and displacement. Principle of work and energy. Consider the particle in the figure, this particle, which is located on the path defined relative to an inertial coordinate system, that is the X, Y, and Z coordinate system. So if the particle has a mass m and is subjected to a system of external forces, and those forces are represented by resultant force Fr, which is called to summation F, then the equation of motion of the particle in the tangential direction, that is F, will be equal to MAT. That's in this direction. This is the tangential direction. So applying the kinematic equation, AT equals V dV over ds. So, and integrating both sides, assuming initially that the particle has a position S is equal to S1, and then at that the position S is equal to S1 has a speed V is equal to V1, and at position S is equal to S2, then V is equal to V2. Then we have that summation integral Ft ds is equal to integral Mv dv. What we are saying is this. F is equal to MAT, which is equal to M V dV over ds. So the S will be taken to this side. So we now have Ft ds is equal to Mv dV. Then we now integrate. Because M is a constant, so we'll take M outside the integral. So that now, and then when we now integrate between the limits of V1 and V2, we have this. So from the figure, we know that summation Ft is summation F cos theta. That is the horizontal component of the total resultant force. And since work is defined from equation 1 as being in the direction of either the in the direction of the force, so as F ds cos theta, then work here is equal to this guy. So this is F cos theta. This is F cos theta. So this equation represents the principle of work and energy for the particle. The term on the left is sum of the work done by all the forces acting on the particle as the particle moves from point 1 to point 2. The two terms on the right side, which are of the form T is equal to half mv squared, defines the particle's final and initial kinetic energy, respectively. So like work, kinetic energy is scalar and has the unit of joule. However, unlike work, which can be either be positive or negative, that is, work can either be positive or negative. Kinetic energy is always positive, regardless of the direction of motion of the particle. This is simple enough that when you have your V, whether your V is positive or your V is negative, by the time you square the V, by the time you square it, by the time you square your V, that is your velocity, then it will become positive. Whether you have negative velocity or you have positive velocity, your kinetic energy will always come out as positive. When equation 6 is applied, it is often expressed in the form of T1 plus all the work done is equal to T2, which states that the particle's initial kinetic energy plus the total work done by all the forces acting on the particle as it moves from its initial position to its final position is equal to the particle's final kinetic energy. So as noted from the derivation, the principle of work and energy represents an integrated form of summation Ft is equal to MET, obtained using the kinematic equation. This kinematic equation, AT equals V dV over ds. So as a result, this principle will provide a convenient substitution for summation Ft is equal to MAT. When solving those types of kinetic problems, which involve force, velocity, and displacement, since these quantities are involved, principle of work and energy for a system of particles. So the principle of work and energy can be extended to include a system of particles isolated within an enclosed region of space as shown in the figure. So here, the arbitrary height particle having a mass mi is subjected to a resultant external force Fi and a resultant internal force Fi, which all the other particles exert on the height particle. If we apply the principle of work and energy to this and each of other particles in the system, then since work and energy are scalar quantities, the equations can be summed algebraically, which means that each particle, we've looked at this, the principle, we apply the principle of work and energy to a particle. Now, we're now going to aggregate all the particles together so that we can now find the equation. So we now say summation T1 plus summation U1 to 2 is equal to summation T2, that is the total kinetic energy, initial kinetic energy, plus the total work done by all the external forces on the system is equal to the total final kinetic energy. In this case, the initial kinetic energy of the system plus the work done by all the external and internal forces acting on the system is equal to the final kinetic energy of the system. So if the system represents a translating rigid body or a series of connected translating bodies, then all the particles in each body will undergo the same displacement. Therefore, the work of all the internal forces will occur in equal but opposite collinear pairs, and so it will cancel out. On the other hand, if the body is assumed to be non-rigid, the particles of the body may be displaced along different paths, and so the energy due to the force interaction will be given off and lost as heat or stored in the body if permanent deformation occur. Work of a friction caused by sliding. Work of friction caused by sliding. A special class of problems will now be investigated, which requires a careful application of one of the equations that we have developed. So this problem involves cases where a body slides over the surface of another body in the presence of friction. So this is a body moving from position 1 to position 2 at velocity v, and the force acting on it is P. So we consider, for example, a block translating a distance s over a rough surface as shown here. So if the applied force P just balances the resultant frictional force, mu nk, then due to equilibrium, a constant velocity v is maintained. And then what we expect that equation 8 can be applied as follows: that this initial kinetic energy plus total work done by all the forces on the system is equal to the final kinetic energy. So indeed, this equation is satisfied if PS, that is force times distance, that is this force times this distance, then is equal to the kinetic friction. This is friction. This is the coefficient of friction. And K means kinetic coefficient of friction. That is when the object is moving, kinetic. So this is the normal reaction of the block to the weight of the block. And then W and N, they are equal and opposite. So S is the distance that the block will move. So indeed, however, as one realizes from experience, the sliding motion will generate heat because of the friction, a form of energy which seems not to be accounted for in the work energy equation. In order to explain this paradox and thereby more closely represents the nature of friction, we should actually model the block so that the surfaces of contact are deformable. That is, they are not rigid. So recall that the rough portions at the bottom of the block act as teeth, and when the block slides, these teeth deform slightly and either breaks off or vibrates as they pull away from teeth at the contacting surface as shown in figure C. So because when we put most surfaces under microscopic examination, we discover that there are soft, rough surfaces. They are actually rough surfaces, no matter how smooth we believe or assume they are. So we will see hills and valleys, and there are rough surfaces. So where you slide them over each other, if not, like if you have a table and you put a book on it, if there's no roughness, like this teeth we are talking about, the book should just slide down or slide to the other side, slide by itself, because it's become frictionless. So as a result, frictional forces that act on the block at this point are displaced slightly due to the localized deformation, and later they are replaced by other frictional forces as other points of contact are made. At any instant, the resultant F of all these frictional forces remains essentially constant, that is mu k n. However, due to many localized deformations, the actual displacement S prime of mu k n is not the same as the displacement S of the applied force. Instead, S prime will be less than S. That is, S prime less than S. And therefore, the external work done by the resultant frictional force will be mu k ns and not mu k ns prime and not mu k ns. The remaining amount of work, mu k n into s minus s prime, manifests itself as an increase in the internal energy of the system, which in fact causes the block's temperature to rise. In summary, this is equal to this. So can be applied to problems involving sliding friction. That is, this equation, half mv squared plus ps minus mu k ns is equal to half mv squared, can be applied to sliding friction. However, it should be fully realized that the work of the resultant frictional force is not represented by this term. Instead, this term represents both the external work of friction, that is mu k ns prime, and internal work of friction, mu k ns minus s prime, which is converted into various forms of internal energies, such as heat. Thank you. End of part B. So do not forget to like, subscribe, share, press the notification bell for new videos, which will be coming up every time. And then if you are one of my university undergraduate students, please do not forget to subscribe with your real name. Thank you, and God bless you.